Now resistances in series, this equivalent relation formula is pretty common, because in between that 1 second and 10 seconds, those 9 seconds, the charge is accumulated here. That cannot be. I just want you to quickly remember a relation that if there are only two resistances in parallel, each of value 5 ohms and each capable of carrying a current of 2 amperes. It says when two resistances are connected in parallel, then the equivalent resistance is 6 by 5 ohms. So the Kershaws laws are there's two laws. There's the voltage rule or the loop rule, and there's the current rule or the junction rule. Suppose if I move the loop in the opposite direction, whatever charge these brought in, that same charge has to go out. Otherwise you would have charge destroyed or created at this junction, which is not possible. This is not potential difference, this is potential. Hi students, welcome to this session here at Infinity Learn by Sri Chaitanya. I'm Aniruddha, your physics faculty, and today we're going to learn about the combination of resistors. Now there's two types of combination that you're quite familiar with. You've even learnt about that back in class 10, which is the series and parallel combination. Now we'll learn about that a bit. We'll move over that pretty quick because it's familiar to most of you. Then we'll even learn about the Kershaws laws and a few tricks that you have to use to solve those questions, those circuit questions in your competitives. Because in your competitives, your Kershaws law questions won't come with long calculations. Okay? So let's get started with the session today. First off, we learn about resistances in series. Now resistances in series, this equivalent relation formula is pretty common. That if you have multiple resistances connected in series, then the equivalent resistance is just the algebraic sum of all of them. But there are a few more key points with regards to this series circuit that you must remember. Firstly, over here, the current through each of these resistors always remains the same. Which means whatever is the current flowing here, I, is the same current flowing through R1, R2 and R3. And this comes about because of the law of conservation of charge. Which means, what is current? Current is essentially charge flowing through it. Whatever charge enters into R1, that same amount of charge has to get out of R2, get out of R1. Because inside R1, charge cannot get destroyed, nor it can be created. So whatever charge enters, the same charge needs to get out from R1. That charge that enters R2, whatever gets into R2 has to get out of R2. That will enter R3 and so on. So since the charge through each of them is same, and even the time has to be the same, because charge enters, 10 units of charge enters in 1 second, and then 10 units are going out in 10 seconds, that does not happen. Because in between that 1 second and 10 seconds, those 9 seconds, the charge is accumulated here. That cannot be. So that is why charge needs to continuously keep flowing. So the current through each of them is the same. What is different in series? The different thing in series is that the potential difference across them may be different. The potential difference may be V1, V2 and V3. Now there is the possibility that V1 is equal to V2 is equal to V3 when the three resistances are same, but if they are not same, then the voltages would be different across each of them. And this V would then be equal to V1 plus V2 plus V3. Because this is essentially, think of this like work done. This is the total work done. Part of that work done is used up in R1. Part of that is used up in R2 and then in R3. The total energy is distributed among the three places. So that is the series. Remember, current remains same, voltage may be different if the resistances are different. Let's move on to the parallel case. In the parallel case, again, I won't dwell too much on this formula because again the inverse relation is known to you. But what I will again tell you to remember is that in the parallel combination, the potential difference remains the same. Why? Because each of these three resistors are effectively connected about the same points. Now potential difference is the difference in potential between 2 points. So as long as the points are this and this, the potential difference is the same, whether you go by this path or this path. So in R1, R2 and R3, since they are connected across the same potentials, the potential difference across each of them will be the same. What will be different here? The current would be different. So if I current comes in, it would split up into I1, I2 and I3. Okay, the current splits up because it's like charge. Charge comes in, charge can split up. That's not a problem with charge. Charge can split up, it can recombine. Just whatever charge came in might have split up, but later on when they recombine, the same charge and the same current needs to flow out. Okay, so this is the parallel combination where potential remains same but currents may be different if the resistances are different. Here too, if the resistances are same, the currents would have been the same. I just want you to quickly remember a relation that if there are only two resistances in parallel, then R equivalent becomes R1 R2 divided by R1 plus R2. Now most of you may know this, but some of you who don't know, for them I'll just give you, always for most intents and purposes you will get two resistances in parallel, then the equivalent is R1 R2 by R1 plus R2. You can even test that by putting it here. Remove these, you'll see R total or R equivalent will be given by this. Okay, let's move on. We have a few questions here. It says we are given several identical resistors, each of value 5 ohms and each capable of carrying a current of 2 amperes. We need to make a combination of these resistances to produce a resistance of 2.5 ohms which can carry a current of 4 amperes. The minimum number of resistances required over here. So first up, what do you know? Do you connect them in series or do you connect them in parallel? Since the equivalent is less than what the original resistances are, you can be damn sure that the resistances have to be connected in parallel. If they are connected in series, since they are added algebraically, the equivalent will always go greater. But in parallel, the equivalent is always less than the least value of resistor that you add in parallel. Okay, so over here we know they have to be connected in parallel. First up, think about how many resistors there you could possibly have. Use this, apply your common sense here instead of going into the elaborate calculation. Let's start with 2. If we have just 2 resistances, if we have just 2 resistors, then what would the equivalent be? The equivalent would be R1 R2 by R1 plus R2, which is 5 into 5, R1 and R2 would be the same, to 5 plus 5, which will give you 2.5 ohms. So this matches. Next thing we need for it to match is this 4 amperes. Each one can carry a current of 2 amperes. So if you have a circuit coming in and it splits up into the parallel, both these resistances are in parallel, then you want 4 amperes coming in here. Now since both resistances would be equal, it will split up exactly equally, which would make it 2 amperes, which is fine for us because we are within the safe limit. So 4 amperes current can come in, can split up into 2 amperes and 2 amperes and flow out. So in both of those conditions, we have matched the equivalent resistance and we have matched the total amount of current it can take. And how many resistors did we need? Only 2. So our correct option is option A here. Again, this is more of proof for you. Don't go into the elaborate calculations, it's more of proof. Just check this quickly and mark it. Don't dwell on this in your JEE, don't waste time here. Next one, N conducting wires, same length of same dimensions, having resistivity 1, 2, 3 all the way till N are connected in series. The equivalent resistivity of the combination is. So first up, these are connected in series. They are all connected in series, which means R equivalent would be equal to R1 plus R2 plus R3 and so on. You go all the way till Rn. Now it's said that they have the same dimensions and we have been given it in terms of resistivity. So let's write it in the resistivity formula. We'll have rho equivalent, the equivalent resistivity, which is what we need to find out, into L by A. Rho L by A is equal to, for R1 rho value is 1, so 1 L by A plus 2 L by A plus 3 L by A, and you carry on till you go to N L by A. Now over here you see this L by A I've kept same. Why? Because it's said that they have the same dimensions. So the length and area would be the same. Now you can cancel out L by A in the LHS and RHS, which will leave you R equivalent, rho equivalent, which is the resistivity, 1 plus 2 plus 3 plus all the way till N. So you're effectively adding up natural numbers till N, and that by basic AP formula you know what the relation for that is N into N plus 1 by 2. Mathematical relation beyond this. Alright, let's move on. Next question. It says when two resistances are connected in parallel, then the equivalent resistance is 6 by 5 ohms. When one of the resistances is removed, then the effective resistance is 2 ohms. We need the resistance of the removed wire. So let's assume originally that the two resistances are R1 and R2. Two resistances, let's draw it out here. We have them connected in parallel. and this is R1, this is R2. Now the equivalent is 6 by 5 ohms, which means 6 by 5 is equal to R1 R2 divided by R1 plus R2. Now suppose I remove this R1. I remove R1. Let's erase it out. If I remove R1, if I remove this R1 here, then it said when I remove the resistance, then the effective resistance is 2 ohms. Now see, if I remove R1, this is neither series nor parallel. This is just one individual resistor now, which means whatever I got as 2 ohm is exactly this. That is all. It's the second resistance resistor has the resistance 2 ohm. Because when you remove one, it just becomes one single resistor. So I know that R2 is 2 ohm. Let's put that in here. 6 by 5 is equal to 2R1 divided by 2 plus R1. So over here, if I put R1 is equal to 3 ohm, see again, use your common sense, be quick in your JEE. You could cross multiply, add, subtract and everything, do tons of things, make the process longer for you. Or you can look at the option, 3 ohms, put it in there. If I put R1 is equal to 3, 2 into 3, 6, 2 plus 3, 5. It matches. So our correct option is 3 ohm. Once you get to the last calculation, try how you can get it faster. Okay, that is the key to saving time in your JEE. Okay, now we move on to the voltage laws, or not the voltage laws, the Kershaws laws. So the Kershaws laws are there's two laws. There's the voltage rule or the loop rule, and there's the current rule or the junction rule. So first up we learn about the voltage rule or the loop rule. Over there, what does Kirchhoff's first law or Kirchhoff's voltage law says? If you have a complete circuit such that it's closed, over here it's a battery, this line is longer, my bad. So if you have a complete circuit, then if you pick any point and you go along that circuit measuring what the potential drops are, what the potential gains are, if you just keep adding them all up, effectively when you come back here, your net potential change should be equal to 0. Now that is easy to say, that's just a theoretical statement. How do I put that in here? See, I am moving, let's say I start from this point on and I am moving in this direction, and this is the direction in which I am moving. This is a hypothetical direction. Needn't be in the direction of current or anything. You can move in any direction you want. I am starting to move in that direction. So while doing that, how do I find what is potential drop, what is potential gain? Look at the rules here. First rule says when moving through the loop in the direction of current, there is a potential drop across a resistor. So when I start from here, I move in that direction, I cross this resistor. When I am crossing this resistor, I am moving in the direction of current. My loop movement is in the direction of current. So the potential, this resistance will give a potential drop. What is that potential drop going to be? It's going to be IR1. It's going to be IR1 because we know V is equal to IR. But it will come with a negative sign because of this first rule here. Then I go to the second part over here, which is, again we come to a resistor. Again my loop is moving in the direction of current, which means it will also come with a negative sign. We put that in, minus IR2. Then we come here and we arrive at this battery. Now my loop is moving upwards, battery also pointing upwards. Look at this rule, the third rule. If a cell is directed in the direction of loop, there is a potential gain across the cell, which means this will give a positive part. What will the positive part be? It will be the EMF of this cell, V2. Now after that I come to this point, and by Kirchhoff's rule, I know since I've made one complete circle, I've taken all the potential drops and gains, so this should be equal to 0. Suppose if I move the loop in the opposite direction, start from the same point but I move in the opposite direction now, then over here V2 is directed opposite to my loop movement. My loop is now moving in this direction, V2 directed opposite to it. Look at the fourth point. If the cell is directed opposite to the direction of loop, there is a potential drop, which means when I am considering the loop in the opposite way, this will come with a minus V2. It will be a negative sign. Then bottom part, nothing's there. You come to this resistance. Over there, you see my loop is moving opposite to current. So this point says when moving opposite to flow of current, there is potential gain across the resistor, which means this IR2 will now come with a positive sign. After that, we again come to this place over here. Again, my loop is still moving opposite to the current, which means this will also give a positive part. And this has to be 0 because I've again come to the starting point. Now see, both of them are same, just with a negative sign. Now over here it did not matter, but for more complicated circuits, you have to be very particular about what is the potential gain, what is the potential drop, based on which direction you are moving the loop. Okay, so be very careful about the laws over here. Fine. Next, let's move on to Kirchhoff's current law. Kirchhoff's current law is also called the Kirchhoff's junction rule, because over here we are dealing with what happens in a junction. This was called a loop rule because we saw what was happening in a loop. Here we deal with what's happening at a junction where many wires meet. So this rule is very simple. It just says that whatever is the current coming in should be equal to the current going out of the junction. So over here, what are the currents coming in? I1 and I2 are coming into this junction, and I4, I5 and I3. I5, I4 and I3, these are going out. So what Kirchhoff's law just says is that I1 plus I2 should be equal to I4 plus I3 plus I4 plus I5. Why? Because again, this comes from the law of conservation of charge. Whatever charge these brought in, that same charge has to go out. Otherwise, you would have charge destroyed or created at this junction, which is not possible. So this is Kirchhoff's current law, just this relation. I'll show you how this Kirchhoff's law will actually help us. Most students think with regards to your boards, only this is important. But in JEE, this also plays an equally important part. We'll even do a question based on that. Occasionally, you will not have complete loops. So over here, Kirchhoff's current law states that for a parallel path, parallel does not mean the lines have to be parallel. It just means that whenever you have branching, you're effectively having parallel combinations. So if you have two resistances here, this is a junction. So a junction generally appears when in a parallel circuit. So for a parallel path, total current entering a circuit junction equal to total current leaving it. I in, summation of I in is equal to summation of I out, and like I said, it comes from the conservation of charge. Alright, so we have done Kirchhoff's current law as well. Now we move on to the questions. This one says we need to find E, this unknown EMF of this loop. This is a complete loop, which means I can write Kirchhoff's voltage equation for this. So let's do that. First up, let's start at this point B. We'll start at B and then circle back to B over here. And I'll move the loop in this direction. Over here, first up, this is the direction of current. This 4 ohm will bring about a negative value. Why? Because I'm moving in the direction of current. So minus 1 ampere current into 4 ohms, so minus 4. Then I have E. This E is directed in the direction of the loop, in the direction in which I'm moving the loop. So this will be plus E. Then I come to this 3 ohm. Over here I'm still moving in the direction of current, which means this will come with a minus 3. 3 into 1, okay? I don't want you to think I'm just putting the resistance. Since the current is 1, that is why I'm just putting 3. It's effectively 3 into 1. Then you come to 10 volt, but this 10 volt is directed opposite. My loop is moving in this direction, 10 volt directed opposite. So this will come with minus 10. Following that, I've come back to 5 volt. 5 volt is directed in the direction of loop going like this, which means this will come with a plus 5. And again you go to 6 ohm, current here is still moving in that direction, in the direction of loop. This will also come with a negative sign. And I've arrived back at point B, which means this complete loop is done. So that is equal to 0. The total is equal to 0. From here you have minus 4, minus 3, minus 7, minus 10 gives it minus 17, plus 5 gives it minus 12, minus 12, minus 6 gives it minus 18. Shift minus 18 that side, keep E on this side, you'll have E is equal to 18. So your correct answer would be 18 volts. Okay. Next, in the galvanometer reading, the galvanometer is 0 in the given circuit. We need to find the value of X. So galvanometer reading 0 over here just means no current passes through that part. Now over here, since there are two cells, you have to use Kirchhoff's laws here. And we'll use that, and I'll show you how for multiple like branched networks here, how you can choose any loops that you want, move in any direction that you want, and you'll still get the relation, you'll still get the final answer correctly. First up, let's choose this loop here and we'll move in this direction. The current, I'm assuming, is flowing over here. Okay, this is I, this is also I, right? Why? Because over here there should have been branching, this should have been I1 and I2, but I already know that over here there is no current flowing. So I know the total current that comes in this junction has to go out from this side since nothing is going from there. So it's all I over here. Now let's put in this loop, I say start from this point. Start from this point, move in this direction. First, this will give you a plus 12 volt. Loop moving in the direction of cell. This will give me minus 500I. Minus 500I. Again, I go here and I get minus xi. And that is equal to 0. My first loop is complete. The next loop that I'll choose is this loop. Just this, starting from here, up, back in this, just this smaller square here. And I'll move the loop in this direction again. When I do that, you see this xi will come with a negative sign. Why? My loop is now moving in the opposite direction to current. So this is what I want you to be careful about. When I wrote this loop, this came with a negative sign. Why? Because the loop was moving in the direction of current. But for this loop, the current is moving opposite to the direction of loop, which means this will now come as plus xi. Here it was minus, here it will be plus. Now there's no other contribution. You go here, galvanometer does nothing because no current there. Even if there's resistance, it doesn't matter. But over here you come to this 2 volt, and this 2 volt is directed opposite to the loop, which means it will come with a negative sign. So you have minus 2 and you come back here and that is equal to 0. That makes xi to be equal to 2. If you put that in here, you will get let's remove this volt. There is no point, it will just confuse us with regards to variables. So we have 12 minus 500i minus 2. So 500i is equal to 10. 500i is equal to 10. So I is equal to 10 divided by 500. Okay. Now xi is equal to 2. Let's do that here. Then if I put the value of I here, x would be equal to 2 by I. So 2 by 10 into 500. Let's cancel this out. You have 2 into 50, that is equal to 100. So x is equal to 100 ohms. That is the correct option. So this is how you operate with the Kirchhoff's voltage rule to find in each case. Now we'll look at a trick. Okay, sometimes you have this and you think it's a complicated circuit, have to use Kirchhoff's law in 1 loop, 2 loop, 3 loops. Don't have to go that. In some cases, you can use a trick. Okay, try to find this trick. This will only come with practice, but I'll show you what the trick is. So see, over here, this is grounded. So I can assume that this point here has a potential, not a potential difference, a potential of 0 volt. If this has a potential of 0 volt, then this point needs to have a potential of 4 volts. Why? Because the potential difference between this and this has to be 4 volts. Because that is what a cell does, it creates a potential difference. So if this is 0, this has to be 4 volts. Now if this is 4 volts, this over here has to be 10 volts. How do I know that? Because the negative potential of this cell is at 4 volts. And I know there should be a potential difference of 6 volts between this point and this point. So this has to be 4 plus 6, 10 volts. So over here I've got 10 volts. Next I come to this point. This point should have a potential of 2 volts. Why? The higher potential is at 10 volts. So the lower potential has to be at 10 minus 8, that is 2 volts. So I've got 2 volts here. Now what have they asked us to find? The current through the 5 ohm resistor. Now see, I don't even have to find the loops and use Kirchhoff's voltage rule here. I know that across this resistor, what is the potential difference? It's 4 minus 2, 2 volts. Potential difference is, let's find the I. I is equal to V by R. I is V by R. What is the potential difference across this? That is 4 minus 2, 2 volts. 2 divided by the resistance, that is 5. That is equal to 0.4 amperes. 0.4 amperes. So see how quickly we were able to solve this. If I wanted to do with the Kirchhoff's rule, I have to write the equation for this, write the equation for another one, then solve it. It's a long process. But if you just use I keep telling you, this will only come with practice. Figuring this trick out will only come with practice. You'll get lots of questions. Even in our Telegram channel, we keep posting questions like this. So if you figure that out, you can solve questions literally in seconds. In less than 10 seconds, you should be able to mark and then get the answer. Alright, let's move on to the next question. Over here, we need to find the current through the 10 ohm resistor in the figure. So we need the current through this resistor over here. Now again, here we'll use the Kershaws Junction rule. But now in your boards, you'll use the voltage rule more commonly, but for JEE, junction rule is equally important. How do I use it? Over here, I assume that the potential of this point is X volts. Potential at this point is 10 volt. This is not potential difference, this is potential. Which means I can have a current coming in, I, that over here I have I1 and over here I have I2. These are the currents in each of the paths. So first up over here I have 10 volts and X volts. So the current I would be equal to 10 minus X divided by 10. So the potential difference divided by resistance. Similarly, I can get for I1 would be equal to X minus 7 divided by 20. 7 divided by 20. See, I am taking X minus 7, but here 10 minus X. Why? Because current always flows from higher to lower potential. So higher to lower. That is why I did 10 minus X. Here, since I see current flowing in that direction, I know X has to be at a higher potential. So I put X minus 7. Next, I2 would be equal to X minus 5 divided by 30 ohms here. 30. Now I use Kershaws junction rule. What do I know by Kershaws junction rule? At this junction, I has to be equal to I1 plus I2. Because current coming in is I, current going out is I1 and I2. So let's put them in. 10 minus X by 10 is equal to X minus 7 by 20 plus X minus 5 by 30. First up, cancel these zeros. These are over here will give you a 6. 2 into 3 will give you a 6. Cross multiply here. That gives you 60 minus 6x. Over here, 3 will cross multiply with this when you're doing the LCM. So this will give you 3x minus 21. Plus this will go here because of the LCM. That will give it 2x minus 10. So let's see, you have 60 here, 21 and 10 come here. So this and over here you have 6x. Okay, so let's write 60 plus 21 plus 10 is 91. And what happens to the x's? You have 3x plus 2x, 5x. 6x goes there as a positive. So 5 plus 6 is 11x. Capital X. So x is 91 by 11. That is the voltage of this point. 91 by 11 volts. This is not our answer yet. We need this I. And this I value we can get from here now that we know X. So let's find that out. Let's create a partition here. And I is equal to 10 minus X, which is 91 by 11, divided by 10. So that is going to give me 110 minus 91 divided by this 11 is not going to come down with 110. That makes it 19 by 110. 19 by 110. So over here, right off the bat, I know this should be the answer. Why do I know that? Because see, point 1 would only have come if this was 11 by 110. Then it would be 1 by 10. Point 2, for point 2 you needed 22 by 110. So the answer 19 by 110 should be between point 1 and point 2. There is only one option here, that is 0.172. So that is how you mark it without even calculating. So that's it with regards to our discussion here of combination of resistors. I've showed you a few tricks, Kirchhoff's laws as well. But the tricks that I showed at the end, they, like I keep saying, this will come second nature to you only with practice. You can get the notes in our Telegram channel. The link would be down in the description. Thank you so much for watching. Catch you all in the next session.